HI is the strongest of the hydrogen halide acids. The next is HBr, the next is HCl, and the least strong of the halides is HF, which is actually a weak acid. Make it stronger as you go down the column. We consider chloride, bromide, and iodine strong acids. That's in water. If you're not doing it in water, you'll find out that iodine is much stronger than the bromide, which is much stronger than the chloride. This HCl, HI is the strongest acid of all of those. HBr is next, then comes HCl, then comes HF. And so as leaving groups, iodine is the best leaving group. This is why I warned you at the beginning, at the end of last lecture, stay away from methyl iodide. Because methyl iodide is the poster child for this reaction. It's got a substrate, which is a methyl group, so there's nothing blocking the back end of the carbon. It's got a fantastic leaving group, so it doesn't take much of a nucleophile to drive off the leaving group and do the reaction and stick the methyl group on something else, like the DNA in your body or anything else inside the cells in your body. So it's a very powerful methylating agent because it's the ideal SN2 combination. So here's the reaction we did. If you take sodium bromide and try to react it with alcohol, nothing happens. It's so slow that virtually nothing happens. So what did we do? You took HBr instead. What is the H going to get you? If you think about it, since OH minus is such a lousy leaving group because it's such a strong base, what we want to try to do is change the nature of the leaving group. And we can do that by using an acid. If I use HBr instead of sodium bromide, what will happen is the proton from the acid will protonate the oxygen. And I'll end up with that thing, the hydronium ion. Now, what's the leaving group? As the Br minus comes in and makes a bond to this metal, what does it have to drive off? Water. Water is a much better leaving group. It's a much weaker base than hydroxide ion. So this reaction works with HBr because I changed the nature of the leaving group. I made it a much better leaving group. The thionyl chloride, the SOCl2, does exactly the same thing. The lone pair on the oxygen in the alcohol attacks the sulfur in the SOCl2, connects to that, and you have and you end up with a much better leaving group. And the same thing with the PBr3. You can look at those mechanisms in this chapter. I'm not going to ask you the mechanisms, but you should know them for next semester. But it's the same idea. Both of those things change the nature of the leaving group. They give you a much better leaving group. So that's one way of speeding up all of these substitution reactions is by messing with the leaving group. So now, if I protonate that oxygen in the alcohol, what's coming off is water. Water is a much better leaving group, and therefore this reaction goes a lot faster in HBr than it does in sodium bromide. One of the standard tricks in organic chemistry, if you want to do a substitution reaction with alcohols, is to use this thing. This is tosyl chloride. It's a toluene molecule, benzene with a methyl group on one side, and it's got a sulfonic acid on the other, sulfonic acid chloride on the other side. If you react this with an alcohol, it essentially displaces the chloride. You lose the Cl and the H, and you end up with this attached to the oxygen. And the reason this works so well is because now, if I attack this carbon atom with a nucleophile, like chloride ion, what has to come off is not OH, but this tosylate group. And that's a fantastic leaving group. So now, if I take some bromide ion and throw it in there, it'll attack the carbon of the methyl group and kick off the tosylate group, and this is a fantastic leaving group. Why is that such a good leaving group? Why is that anion so stable? That's your go-to word. Resonance. There are lots of resonance structures with that. So this thing is a fairly lousy base, and therefore it makes a good leaving group. So the tosylate ion is something you'll see a lot next semester when you want to encourage something like an alcohol, an OH group, to leave the molecule. You have to modify it somewhat because OH tenaciously holds on to what it's attached to. Okay, and did that already. The last thing we have to talk about in terms of the speeds or the nature of an SN2 reaction is the solvent to the reaction. And this is something we don't normally pay a lot of attention to. I warned you as we started to look at some of the reactions that when you look at some of those reactions in McMurray, he'll list the solvent under the arrow. And whether or not that really means a lot really depends on the specific reaction. Sometimes it's just a good solvent that all the reactants will dissolve in. Sometimes the solvent is critical to the reaction, like THF with the BH3, because THF stabilizes the BH3. That was an important solvent that actually takes part in the reaction. But in fact, in many cases, especially in SN2 reactions, it turns out the solvent you do the reaction in is critical. And in terms of solvent, we can really break them down into two general groups, polar and non-polar. For SN2 reactions, we tend to want polar solvents because we're generally dealing with things with charges. Usually the nucleophile will have a negative charge. Even if it doesn't, very often the leaving group is going to have a negative charge when you kick it off. And so there are charged species. You're actually developing charge in the transition state. So the more you stabilize the developing charge in the transition state, the easier it'll be to form. So generally we stick with polar solvents. They also will dissolve the ions and the salts that we use that we're doing the reaction with. And if we do this reaction, if we have a cyanide ion and we use it to attack methyl iodide to make the cyanide compound, methyl cyanide, and kick off the iodine. If you do this in a polar solvent like ethanol, this reaction will take about an hour, and after an hour, about 90% of it will have been done. So it's not terribly slow, but it's not terribly fast either. If you do this reaction in acetone, which is also a